Today's topic is Lenzs Law, and to understand Lenzs Law, we have to understand few basic things. So in the last lecture, we have studied the electromagnetic induction and Faraday's experiment, and from there we have seen that the EMF produced by electromagnetic induction is equal to minus N d phi by dt. The phi by dt is rate of change of magnetic flux, and here we saw this negative sign, and this negative sign is from Lenz's law. So let us now study what is Lenz's law. First, let us go to the statement. The statement says that the polarity of induced EMF is such that the current produced by it opposes the cause. So in electromagnetic induction, we see that by the changing magnetic flux there is induced EMF, and that induced EMF will produce the current, and the Lenz's law says that the produced by it, okay, the cause, the polarity of induced EMF is such that the current produced by it opposes the cause. So the current which is produced by the electromagnetic induction, which is produced by the changing magnetic flux, that current will oppose the cause, which is my Lenz's law. Okay, so don't get confused, we will study this in detail. So what is cause? Cause, I have written this in the square bracket, which is not necessary. The cause is that magnetic flux which produce induced current. So what is cause? The magnetic flux. Okay, the changing magnetic flux will induce the current, so that is the cause which is opposed by the current. So don't get to this, okay. Whenever we go to this example, then we will understand very well. So this is first example. Now say, let us consider case 1 and case 2. First, case 1. So we have a bar magnet, okay. There is my bar magnet. One is this, another is this. So this is my north pole, this is my north pole, and this is first. And whenever this bar magnet is here, there are so many magnetic field lines, and these magnetic field lines are not linked with this coil now, right? Only the magnetic field which is going from the center is reaching here. What does this mean is that there is less magnetic flux when the magnetic field is bar magnet is here. So this magnetic flux phi is less, which is linked with the coil. Now I move this from this position to that position. I will move it in this direction, and I reach this is my second position. Now whenever I move towards the coil, then what we see is these many magnetic field lines are now linked with this coil. So the magnetic flux linked with the coil is more. So this is flux is more linked with the coil. When it is more, whenever we bring this close to the coil, because whenever it was here, these were not passing through this coil, so it was less. Whenever I move it here, this was more. So what does this mean is here, first of all, so the magnetic flux, okay, the external I will write, external magnetic field or flux is more, or say increasing. Very important, isn't it? Whenever I move it from this, the magnetic field will keep on increasing, isn't it? The magnetic flux will keep on increasing linked with the coil. Okay, so this is one thing. Now Lenz's law says that whenever electromagnetic induction will happen there, therefore there will be a production of current in the coil, because there is increasing magnetic flux. When we move towards the coil, there is increasing magnetic flux. Because of that, there will be induced current, and that induced current have two possible directions. Either it may move in anti-clockwise direction, or it may move in the clockwise direction. Now how to decide that? This is decided by Lenz's law. Now Lenz's law says that the such that the current produced by it opposes the cause. It means that the current which is produced in this coil by electromagnetic induction should oppose the cause. What is the cause? The movement of the magnetic field, and the changing magnetic flux is the cause. Okay. So to oppose this, what is happening here? Let us see. It is going that side. Now to oppose this going that side, what it should do? It should repel, isn't it? It should repel it backward. That is opposition. Okay. So it means that to repel, to oppose this to the backward. Okay. According to Lenzs law, it should oppose. Whenever I moving that side, Lenzs law said it should oppose me, and it should push me back. It will give me backward force. It should repel. Now to repel this bar magnet, which pole should be here? There should be a north pole, because north pole and north pole will repel. To oppose this, then there should be a north pole. So this is my north pole, like this and this, isn't it? Now if it is north pole, then this north pole will give what? Give this direction of magnetic field. Okay, and this magnetic field, red line magnetic field, is the magnetic field produced by the induced current, isn't it? We know current will produce the magnetic field, and this will be the direction of magnetic field produced by the induced current, because according to Lenzs law, it has to oppose the cause. To oppose the cause, it has to repel, and to repel, there must be the north pole, and this north pole and this north pole will repel, and Lenzs law is successful. Because of that, there is negative sign. Then what should be the direction of current here? It is anti-clockwise. North pole means anti-clockwise. Okay, the direction of current is from this direction, I. Okay, this is 1, not I. It is going from backward and coming towards us like this. So this is the direction of current. So I will write here anti-clockwise direction. Now we see the thing. When the external magnetic field or when the external magnetic flux is increasing. Why it was increasing? It was increasing because we are moving towards the coil. Very less was here because this 2 was not linked with the coil. That is less. Whenever I go closer and closer, the magnetic field lines or the flux is linked with this coil, and there is flux is more or increasing. Then whenever there is increasing external magnetic flux, then what should be there? This is the magnetic field, induced magnetic field. Okay, and the direction of induced magnetic field is opposite to external, isn't it? This is external magnetic field going that side, blue one, and red is the magnetic field produced by induced current is in this direction. So red is in this direction, blue is in this direction. They are opposite. So this is very important concept. If you don't remember this, you won't be able to answer any question. Then the induced magnetic field is opposite to external magnetic field. This is very important. Okay, if you remember this, then we can solve any type of question. External magnetic field is increasing. I have told you it is going that side, so it is increasing. Then the induced magnetic field is opposite to external magnetic. Very important. If the external flux is increasing, then induced magnetic field is opposite. Increasing, opposite. Increasing, opposite. Increase what? The opposite. Why? Because of the Lenz's law. Now let us go to the second case. Now second case, again this is my north pole and this is my south pole. Okay, no, this is again the north pole. Now this is first case and this is my second case. It means that I am going from this to this side. Okay. First the bar magnet was here and there were 3 magnetic field lines linked with this coil. So here what happens is magnetic flux is more. Okay, and whenever I move it backward, whenever I move away from this coil, then there is less magnetic flux here, because this magnetic flux is going like this, which is not linked with this, then here is my flux is less. Okay, so what does this mean is that whenever I move away, then there is a external magnetic field or flux is decreasing. Very important. Why I am going away? Now, whenever there is decreasing, then what will happen is either it is increasing or either it is decreasing. There is change. Change means to decrease or to increase. Now, if there is increase or decrease of magnetic flux, there should be again what? Induced EMF and the induced current due to electromagnetic induction. Okay, electromagnetic induction will happen. Either the magnetic flux will increase, either the magnetic flux will decrease, doesn't matter. Okay, so there has to be electromagnetic induction, so there will be induced current. Now again, what should be the direction of induced current? Of course, it was anti-clockwise, then it should be clockwise. Let us decide it with the help of the Lenzs law. So according to again Lenzs law, it has to oppose. Now in this case, the bar magnet is going away. Then to oppose it, what should it do? It was going away. To oppose this, according to Lenzs law, it has to attract that side. It was going that side. According to Lenzs law, it has to attract. Then to attract it, which pole should be here? Here should be south pole, right? So here it should be a south pole like this and like this. Okay, we have understood this. So if there is south pole, then this north pole will be attracted because it was going away, and to oppose it has to attract. Okay, and one more important thing is that whenever there is flowing current in any coil, one side will look like a north pole, another side will look like a south pole. We have studied this in chapter 5. So if it is south pole, then what will happen? In the south pole, the magnetic field will go in this direction, this black, right? We know from north pole the magnetic field will come out, and to the south pole it will go down. Now, what is the direction of the magnetic field? Are they same or opposite? The external magnetic field is blue here, and the magnetic field produced by induced current, that is black, is also in the same line. Okay, so whenever the external flux is decreasing, why it was decreasing? It was decreasing because it was going away. Then same as this. Okay, then induced magnetic field is in the same direction with external magnetic field. So these two are very, very important concepts. Okay. If the magnetic flux is decreasing, then the induced magnetic field is in the same direction with the external magnetic field. Example, blue is this, black is this. So they are in the same direction. External and induced magnetic field is in the same direction. When it happens? When the flux is decreasing. And when the flux is increasing, there should be opposite direction. Okay, induced magnetic field should be opposite to the external magnetic field. And please remember, we have to remember this too. If we do not remember this, then we won't be able to answer any question. So please remember, external increasing, induced magnetic field opposite, increasing opposite. Okay, decreasing same, increasing opposite, decreasing same. Okay, you have to understand this.